For all you playing at home, this is page 217, approximately in your notebook. It's 217 this year, but who knows next year? There could be new and exciting things added. Yeah, you're going to watch that game show version of me. So we have the schedule up here. Today we're doing the notes, and shocker, after we do the notes, I'd like you to try to do worksheet 1. And then next class we'll go over worksheet 1. Today, this year, today's the 13th. Next class would be the 15th. Then we have a weekend. Then I think it's the 19th and the 21st. That's just for B days. If you're in a different year, none of that applies to you. But it does apply the schedule-wise. It's about 4 classes. On the 4th day, there is a test, and you need to show that you know the stuff you do or do not know. This is also, in this year, the last test this quarter. So if it's a different year than this year, meh, that might not apply to you. But for us this quarter, this is the last test. Pause. This is actually a pretty easy chapter. If you try a little bit, it has a little bit of math, a little bit of vocabulary. Make sure you can master both. If you look at the vocabulary down here, there's a couple terms you probably have never seen before. Arrhenius acid and base. What's that? Bronsted and Lowry. I thought that was a salt seasoning or something. It's acid and base. Electrolytes. Gatorade. We'll talk about those later. pH and POH. What is Poh? I know what Ph is, but what the heck is a Poh? Kung Fu Panda. That was good. I actually got your joke for once. Indicator, litmus paper, and titration. You guys have seen litmus paper. It's a little piece of paper you stick in the acid. It turns blue or it turns red. You're like, woo, that's red now. We'll explain how that works. Indicators are kind of like litmus paper, but more in a liquid form. And titration, that's how that's pronounced, titration. Before we get to that, though, we should probably review some things that would be key skills. This is not in your notebook. Don't stop flipping in Homeland. Just here on the screen. And the audience here in front of me is going to try to participate. Which one of these is an acid? Yes, Klaus. Pick one, yes. Number 2 is an acid because why? It starts with a hydrogen, right. Augustus Luke. No, that's not your name. Jeff, you got an acid? Number 3, yes, starts with a hydrogen. And I'm trying to remember your name. No. All right, anyway. What are the other acids? 4 and 6. They start with hydrogen. They must be an acid. If you don't know your nomenclature rules, that was Chapter 4, nomenclature, back in like October. If you want to watch some videos because you're having trouble sleeping at night, there are 4 YouTube videos on nomenclature by this horrible voice. And they start with, how do you figure out what category you're dealing with? You all identify the acid category because they start with hydrogen, but there's also molecules and ionics. Remember those days? Those videos exist out there if you need to watch them. Let's review the acid rules. There was a silly little phrase we used to say, 8-ic, ite, us, and then hydro, blankic, yeah. And that was kind of our 3 shorthands for those rules. 8-ic, that would apply here. What is SO4? Sulfate. So it changes to sulfic or sulfuric? Sulfuric. Yeah, it's sulfuric. A lot of times we make little changes to the rule, and they decided instead of saying sulfic, they'd say sulfuric because it just sounds a little bit better. What is this element? Sulfur. So the first rule doesn't work because that's 8. The second rule doesn't work because that's 8. So the sulfur gets tossed in the blank there. Hydrosulfuric acid. H3PO4. What's PO4? Phosphate. Phosphate is phosphoric or phosphic? Phosphoric acid. And then the last one, we just have the col here. That's going to go in the blank, isn't it? Hydrochloric word. All right, so those were our acid rules using the 8-ic, ite-us, hydro-blankic. The next couple questions are what we're going to call bases. And it's not all about the base, but it is rather important. Bases have, guess what polyatomic ion? Hydroxide. That's why I underlined it in each one of those there. Do you see it? Hydroxide, hydroxide, hydroxide. And the names for ionic compounds were pretty simple. You said the name of the first element, sodium, and then you said the name of the second element or polyatomic ion, hydroxide. So this one on here is also calcium hydroxide. Hey, Mr. Murphy. Yes. Jeff. But there's a 2 there. How are we going to show that 2? Well, when we did ionic compounds, we grabbed charges from the periodic table. We're like +1, +2, Roman numeral land, +3. Remember the Roman numeral land where like the charges were all wacky? There's an example of that right here. Iron is in the middle of Roman numeral land, so you have to figure out its charge. Its name is iron something hydroxide, and you have to tell people, well, that's nice and illegible. You have to tell people what the charge is, and the trick to telling the charge, I'm very confused. Anyone else confused right now? All right. A stranger just walked into the classroom. He's dropping, oh my God, that's a calculator. Okay. So you have to write down the stuff we do know. We have hydroxide as a -1. There's 3 of them. There's 1 iron. If this is a -1 and there's 3 of them and there's 1 iron, what's the missing charge? Yeah, 3. And so we would say Roman numeral 3 because that is a missing 3. So we had to fill in some of the missing pieces. Have I done them all? I skipped the third category. The third category is molecules, not pronounced molecules, but molecules. And with molecules, you got to use prefixes. What was the prefix for 1? Mono, right. That's what you hope to not get, right? And what's the prefix for 2? Di. Yeah, don't tell that to me, though. What's the prefix for 3? That's all I ask you to do is try. 4 is usually the hardest one. Tetra. Tetra is the one a lot of people are like, I don't know. So tetra was 4. So here we have 1 nitrogen and 3 hydrogens. The name of this fancy molecule is nitrogen, tri, and then they messed up the ending a whole lot. They changed it to IDE, so hydrogen became hydride. Not hydrogenide, but hydride. This molecule also has a common name. There's typically only 2 molecules chemists are happy with you using the common name. Dihydrogen monoxide is usually called water. Nitrogen trihydride is usually called ammonia because they're very common, simple molecules that are used all the time in chemistry. So ammonia, pause for this. Yeah, that's probably the best joke I'm going to tell all year. Anyway, so we're going to get right into acids and bases now. Here we have the standard pH scale. This is not in your notes. This is more like a review of your biology pH introduction. Remember you learned pH in biology? And basically we're like, if it's close to 2 or stuff, don't touch. It'll burn you. That's not false, but it doesn't really explain what's going on. We're going to try to get into what pH really means today. First of all, pH for the most part goes from 0 to 14. We will break the scale and go beyond it in both directions. We'll have negative pHs. The world record for negative pH is -31.5. It's an insane acid that's used to etch metals. So you put that acid in metals and you can write things into the metal with it because it burns through the metal. Thankfully, we don't have that. We can't even contain it if we did. The strongest acid we have is a -1.5. But that is right off the scale. Normally it goes from 0 to 14. Which side is dangerous, 0 or 14? Both sides. There's only one safe spot, and that's kind of here in the middle. Around 7 is where you have water, milk, sodas, blood. Yes, blood is safe, just disgusting. That's most of the things that are okay to be around are right there in the middle. As you get farther away, you might notice that there are some things that people do drink in the acidic side, but eventually you get too acidic. When you hit like 2, it's starting to get dangerous. Has anyone ever gotten lemon juice in an open cut? That hurts, doesn't it? You know it immediately. It's got some acid in it. On the other side, has anyone had to drink milk of magnesia for an upset stomach? If you have a lot of acid going on in your stomach for some reason, milk of magnesia is a safe grocery store item you can buy and drink, and it neutralizes the acid and settles your upset tum-tum. All right. Later on, I've got a brief story about a guy falling into an acid spring. That'll be fun. But the strong acids are on the extreme sides. Those are the things you definitely don't want to touch. If someone tells you it's a pH of 2 or lower or 12 or higher, you want to keep it off your hands. All right? We don't wear gloves in chemistry unless it's a carcinogen. So when I work with acids and bases, I work with my hands, not gloves. Gloves reduce your dexterity, your ability to control things, your ability to pour. You don't want to have poor pouring skills while dealing with dangerous things. You really want to have it under control. So when Mr. Shangraw, Mrs. Hoffman, and I deal with our strong concentrated acids, we're doing it in our hands. Not on our hands, but we're using our hands, not gloves, because it's the safest way. Things you also got introduced to in biology was litmus paper. Litmus paper turns red in an acid and blue in a base. And the way I remembered this was right here. Blue, base, both start with the letter B. Yeah, it's like a book about bees, and somehow they left that off. But the blue base litmus paper, I could never remember litmus paper was red and acid. I just remembered base was blue, and then the opposite must be the opposite. Also, taste-wise, acids tend to taste sour. You ever had a lemon in your mouth? That extreme sour flavor? Meh. Bases tend to feel slippery. That's partly because they're reacting with your skin and turning it into soap. We can get into that a little bit later. They react with the oils in your skin, and the base plus the oils make something similar to soap. It is soap slippery? Right, so it's actually kind of creating soap on your skin in not a good way. I'm going to pause for a second as I talk. Okay, and now we're finally on the notes. So in the notes, you see the definition for Arrhenius acids and bases. What page am I on? 219? Thank you. Not 2019, but 219, yeah. Anyway, Arrhenius acids and bases. I've got the hiccups. Fantastic. Arrhenius was our first kind of person that studied acids and bases. And this definition's pretty good, but it's not perfect. In the Arrhenius definition, acids give off hydrogen. So if you put an acid into water, the acid breaks apart, and now there's a lot of hydrogen floating around. Cool? These hydrogen ions are in the water, and if you spill that water on your skin, it's the hydrogen ions that burn your skin. If it's a base, you put the base into water, and instead of hydrogen, it makes hydroxide. And so those base goes into water, and there's hydroxides floating around in the water, and they can burn you just as much as an acid can, but kind of chemically in the reverse way. So that's what the Arrhenius definition was. It was about hydrogen or hydroxide being freed. However, that definition's pretty limited. There's a lot of exotic acids and bases out there that are more complex. In order to talk about those other acids, we need to really focus all the way back on what the heck a hydrogen atom is. What is a hydrogen atom's number of protons, neutrons, and electrons? Find hydrogen on a periodic table. How many protons does it have? 1. What is the mass of a hydrogen atom? I don't know if you remember this, but mass equals protons plus neutrons. So 1 equals 1 plus 0. So there are no neutrons in a hydrogen atom. It's 1 proton. Usually it also has an electron flying around it. 1 proton, 1 electron. If, however, it's got a positive 1 charge, that means it lost its electron. So let me get this straight. Usually there's a proton, and flying around it there's an electron. That electron gets taken, what's left? a proton. So if you have hydrogen plus 1, all you really have is a proton. Well, let's think about what the heck is water's formula. H2O. And we've drawn water about 1,000 times. We have these two hydrogens, and it's sharing electrons, right, between the hydrogen and the oxygen. Well, if hydrogen's electron is there, what is actually the H? It's not a hydrogen atom. It's a proton. Really, all that's here is a proton. It's an oxygen with two protons next to it, around it, which is one of the reasons water is so weird, is it's actually one atom surrounded by protons. And so those protons grab onto other water molecules really intensely because they have just a positive charge. So Bronsted and Lowry are a team that look at unique acids and bases and how they react with water. And so the definition of an acid and base is a bit more complex. And I'm going to use this spiked ball as a representation of an acid and base. Can you catch back there? If I throw this spiked ball at you, you can catch it? Okay. So the acid gives off a hydrogen. It gives off a hydrogen. And the base receives it. Did I just donate my hydrogen? Did he receive it? So I was the acid. He was the base. On paper, this funny acid is giving away a hydrogen to the water. So does he have one more hydrogen now? He is now H3O because he has one more hydrogen. And don't forget, that hydrogen has a positive charge, so he is positive now. Cool? I lost the hydrogen. Look at me now. I'm just A minus, right? Sounds like my grade in chemistry. Good? Ah, yes, the tissue. It'll save you. A minus, the hydrogen's moving. Could you give me that hydrogen back? All right, without hitting anyone in the head, because it's a spiked ball. Nice toss. He's a good partner. Now, when he gave it back, he's an acid when he gives it back. He's getting rid of a hydrogen. That makes him an acid. But, I almost threw it at him and his head was down. I'm going to keep throwing it back to you, so don't look down too often. Anytime I give it away, I'm an acid. Anytime he gives it away, no, I don't want to throw it at Hoodie over there. Throw it at Hoodie, bounce right off. All right, so they can go back and forth. I need you to squeeze in another equation right here. B plus H2O makes OH and HB plus. So this is a similar idea, but it's from a base's perspective, where the base goes in the water and the base takes a hydrogen. Because it's reversible. I can throw you the marker and you can throw the marker back to me. It's our first reversible reaction. Yeah, it's the first time we've seen a reversible reaction. That's not to say some of them haven't been. We just have been pretending they only went one way. Probably the most common reversible reaction is the opening of a soda. You open it, and the carbon dioxide comes out. You can reverse it. You can put the carbon dioxide back in and re-acidify the soda. So this is the same idea, except this is a base. So what is the base doing to water? It took a hydrogen off, didn't it? So base plus water makes hydroxide because the hydrogen's been taken, and now the base has the hydrogen. So here we're going to look at another example. Is the order the same here as it was on that last example? This is the acid, HA. This is the water. And this is the anion, and that's the H3O. Is it in the exact same order as the previous example I just gave you? On this side, doesn't the example have H3O and A on yours? That it doesn't matter what order they're in. That's the only point I'm trying to make, is that A could come first and H3O could come second on the product side. All right. Same thing over here. These could be switched around. It's still the same idea. Really, we're just showing a hydrogen shifting from one molecule to the other molecule. That's acetic acid. Have any of you all ever tasted acetic acid? What's it in? Close. Close. It's in vinegar. Yeah, it's in vinegar. Could be in salt. Could be in salt and vinegar chips. All right. So we're going to pause the video while you all try to take this acid and go to water. Oh, wait. One last thing before I get away from pause. I have 2 hydrogens. Haha. You ready? Psych. We only give 1 hydrogen away at a time. The other hydrogen stays here. So before, I was H2 something. Let's say H2SO4. Pretend I'm H2SO4. You only give 1 hydrogen away. What am I now that I've given 1 away? All right, write that down. Figure out the... Now, I have no hydrogens. Jimmy, throw me the marker. Throw it to me, Jimmy. Why can't you throw me a marker? You don't have one. The CO3 has to be a base because it can't throw what you don't have. All right, I'm going to pause while you guys work out the right side. So most people do a good job moving the hydrogen. You're only allowed to move 1. I had to correct a couple people. Mr. Salt, you did a good job, but your buddy Jeff, he moved 2. So you can only move 1 hydrogen. And when you move the hydrogen, you're moving its positive charge. So these are the right 2 answers. I take a hydrogen off. The charge goes down by 1 because I lost a positive. I add that charge to the water, and I add that hydrogen to the water. Move the hydrogen and the charge. And the second one, the CO3 has to be the base because it doesn't have a hydrogen. Can't give away what you don't have. And so it takes the hydrogen off of the water, creating hydroxide. And hydroxide was the component in that first definition of a base. We said if there's hydroxide, it's a base. Well, this definition of base is different. This definition of base, glad I'm recording this. Yeah, it's definitely a biggie. No one understands what's not going to who. So in this case, the base is removing hydrogen to make hydroxide. It's making it through a reaction. Jeff. So the conjugate went from a -2. If it gains a +1, what is -2 + 1? -1. Why is this called the conjugate acid? Because while this could go, you got good hands, Hoodie? This could go forward. Could it also go backwards? Yep. Yes, it could. Forward, receiving the hydrogen. Backwards, losing the hydrogen. So as it goes backwards and gives it away, it's acting like an acid. When it goes forward, it's acting like a base. When it goes backwards, it's acting like an acid. This is actually an acid you've seen before polyatomic ion-wise. Does anybody remember that polyatomic ion? Bicarbonate. That's bicarbonate. This one was carbonate. That's sulfate with the hydrogen on front. All right. Let's write down some of these simple little names. H3O is hydronium. What is OH? Hydroxide. H plus can be a hydrogen ion. What's another name for H plus? Proton. Yep. Also called a proton. Hydronium, hydroxide, hydrogen ion, or proton. And when you're actually measuring how strong the pH of something is, you're actually measuring how much hydronium is in the water. You don't want a lot of hydronium in your water. That's bad. Okay. So this is pretty easy. This is kind of ignoring the other side. We're saying, hey, turn this into a conjugate base. Take a hydrogen off. How many hydrogens should we take off? One at a time. And we'll get into more about why we only take one at a time in just a second. On the other side, these two things are acting like bases, and I'm supposed to write their acid form. So I'm going to add how many hydrogens to them if I'm writing their acid form? Still just one. We only move one around at a time. And when I add the acid, I'm also adding a positive charge. The -2 plus 1 is a -1. And this one, oops, that's not the letter I meant to make. Adding one hydrogen, and after I add the positive charge, it's at 0. Pregunta? You are absolutely accurate, Mr. Hood. It's SO3. You're right. I messed up. Yeah, the oxygen doesn't change, just the hydrogen. And that's one of the things that's easy about this chapter, is it's one hydrogen changing. Okay? Even if you have phosphoric acid has a whole lot of where are all my hydrogens? They're there. Phosphoric acid has 3 hydrogens, which to a lot of people means, man, I'm really going to get burned. And not as bad as one of Mr. Murphy's jokes, but burned nonetheless. Yeah, I see that very angry face over there. So, phosphoric acid spills on you. You are burned. Phosphoric acid has 3 hydrogens. You are burned. Good reactions. Caught it way down there between his legs. Phosphoric acid spills on you. You are burned. But in reality, even though phosphoric acid has 3 hydrogens, it doesn't give the third one away, ever. It rarely gives the second one away. It's like, hey, you want to borrow this? Not today. The first one, pretty common. It almost gives all of the first one away. So if you have like 2 molar phosphoric acid, it's going to give away 2 moles of hydrogen. It's going to keep the other to itself, though. So that's called a multiprotic acid. Here's a diprotic acid. Why do you think this one's called a diprotic acid? 2 hydrogens, and another word for hydrogen is proton. What's got 2 it can give away. Anytime there's multiple hydrogens, they sometimes give away more than they really need to. We don't get too much into strong acids and bases, so we're not going to right now. So the short version of that is don't fall in a hot spring. Okay? It's a bad choice. It's a bad choice. But I'm really glad we're recording that beeping sound. Glad I turned it back on for that. That's good. All right, so now we got to switch to the math. I have all of the math equations written on the board right now. Let me just edit this one. These are very plug and chug equations. We're going to review how to do logs in a second because most of you hate logs, right? Show of hands who hates logs, right? Okay. You would, but you don't know what they are? Okay. Logs. We're going to do logs in a minute, but I'm going to explain it in a way where it might make sense. Wouldn't that be nice? So a lot of people don't quite understand logs. But before we get to that, this is a multiplication problem. This is hydrogen's value times hydroxide equals 1 times 10 to the minus 14. That value is a constant. It's called the water constant. Do constants change? That's why they're called constants. They don't change. They are constant. So anytime you multiply hydrogen times hydroxide, you should get that value. I skipped a step. My fault. When you see brackets, that's our good old friend molarity. So write that somewhere in your notes. Anytime there's brackets, that's actually molarity. All right? So if I was doing let's say an easy problem here. Let's say Bridget has 5 molar hydrochloric acid. Bridget has 5 molar hydrochloric acid. How much hydrogen do you think is in there? 5 molar, right? And so we could take that 5 and we plug that 5 in right where the hydrogen is. Could we find out how much hydroxide Bridget has? 5 times something equals that value. In scientific notation, I was pretty consistent about using, hey, if you use parentheses, the calculator will less likely to make a mistake. Let's keep that going. Throw parentheses around things so that your calculator does the math the way you want it to. Cool? So anytime you see brackets, that's actually molarity. But instead of writing, what's the molarity of hydrogen times the molarity of hydroxide, they go brackets hydrogen, brackets hydroxide. So it's a little bit easier. I'm going to go in slow motion across one of these. So let's go. I can censor your view. Purple, black. There we go. It's hard to see though. I know it's hard. You can see it. But so let's say that Mrs. Gloop has a hydroxide solution. All right? Inside any water solution, there is both hydrogen and hydroxide. If it's pure water, the hydrogen and the hydroxide should be equal. What does H and OH combine together? H2O, right, two waters. So they're equal values. If, however, she adds some hydroxide, guess what happens to the amount of hydrogen? It goes down. They always go in opposite directions. And we can easily solve for the amount of the other thing. So if we have the amount of hydroxide, I can just squeeze that right into the correct spot on the equation. Why did I put it here? Because it's hydroxide. So where the hydroxide is, now I have hydrogen times hydroxide equals 1 times 10 to the minus 14. How do I solve for hydrogen? If it's multiplication, I divide. So I divided that value to the other side, and that's what's going on here. I'm just going to make it more obvious. This is 1 times 10 to the minus 14 divided by 1 times 10 to the minus 5th. And I would like you to use your graphing calculators for 5 seconds and test that that is the right answer. This is really a can I do scientific notation test again. That's not the problem. It always stinks. Okay. So yeah, it is division. Make sure you're dividing, not multiplying. That you use parentheses around all of these weird exponential numbers. We are going to have other numbers than 1. It will get a little bit odder than that. But now we got 1 divided by that. I have the amount of hydrogen. Which value is bigger? 10 to the minus 9 hydrogen or 10 to the minus 5th hydroxide? And let's remember that's 0.00000. That's 4 zeros. This is 0.0000000. That's 8 zeros. So it's more zeros before you get to the 1. So that's a smaller number. In the second example, the hydroxide is 10 to the minus 7. You go through the math. The hydrogen is 10 to the minus 7. If they're both 10 to the minus 7, which one is bigger? They're equal. What do we call it when the acid and the base are equal? Neutral. Klaus, what is the pH at neutral? And check this out. That molarity is 10 to the minus 7, and the pH at neutral is 7. The pH is actually a reference to that value. And we'll get into that more in just a second. And then this person has really strong acid. 10 molar is a frightening amount. When we buy our concentrated acid, the strongest we have is 18. So 10 is still really strong. And then when they went to solve for the amount of hydroxide, it's practically nothing. Remember, that's 0.000000001. That's a really tiny amount. So there's a lot of acid in there, very little base. That's a very acidic solution. We'll get into how to calculate, but that would be a pH of -1. Okay? So before we get into doing logs, we're going to briefly re-explain what logs are. For a second, I want you to do a couple of stupid math problems I know you know the answer to in your calculator. Type 10 times 10 in your calculator. How many 10s did you just multiply? 2. Now, right beside the number 7 is log, right? Push log, and then type in 100. You should get 2, because how many 100s are in, how many 10s are in 100? 2. It's 10 times 10, right? When you take a log, you're telling someone how many times the number 10 has been multiplied. You took the log of 10, not the log of 100. How many 10s are in the number 10? 1. All right, now let's type 1,000. Log 1,000. Is it 3? Okay, so here's where it gets a little bit more confusing. Let's do log of 2,000. It's just a little bit above 3, isn't it? 3 point something, 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 something. Okay, why is it not a whole number? Because 2,000 is not 10 times 10 times 10. It's 10 times 10 times 10 times 2. A little bit more than, right? It's got a little bit extra. So you see a little bit above 3 in the answer. And it's hard to figure out what that other thing is going to be, which is why it's great that we have calculators, because they can take a log for us. We don't typically work in huge numbers. We typically work in super tiny numbers. Type this in your calculator. One last thing. This one's a little bit more odd. Log 1 over 10, as in 1/10. -1, right? -1. Because there aren't any 10s, it's actually the inverse of 10. It's 1 over 10, so you're getting -1 as the answer. The pH scale is actually a log scale, meaning that every value is 10 times different. If I move from a pH of 6, let's say that Jeff here is 6, Mr. Salt is 5, that's not actually a difference of 1. He is 10 times more dangerous, which I think we agree. Mr. Salt is 10 times more dangerous than you, or Jeff. And then we have Francine, 6, 5, 4. If she's a 4, she's 10 times more dangerous than Mr. Salt. She's 10 times 10 times, also known as 100 times more dangerous than Jeff. All right? Then we have Jimbo back there, 6, 5, 4, 3. If you're a pH of 3, 10 times, 1,000 times more dangerous than Jeff, and I agree, 1,000 more times dangerous than Jeff. All right? Every time you change on the pH scale by 1, you're actually multiplying by 10. Cool? That's a weird scale, isn't it? Why do they do that? Because you're actually doing molarities. When your pool boy takes the pH, when the pool boy takes the pH, he is actually taking the molarity of the solution. The pool is the solution. So let's say he takes the pH, and he finds out that the molarity is 1 times 10 to the minus 9th. That number means almost nothing to most people, doesn't it? So that's not what he finds out. He takes the pool's pH, and a little bit of math is done ahead of time. It does the negative log. This is the equation. pH equals negative log of hydrogen. So take a second, push the negative sign, log, type that number in, make sure you close the parentheses down, and then it will do the fancy math for you. You should get 9 if you do it correctly. Negative log, and then this big number. That's about as hard as logs are going to be in our life, is using an equation and plugging a number in there. Cool? We're not going to be doing log laws. Actually, some of them are represented here. We're not actually going to do them. You guys remember those log laws, or having to learn the log laws? How many of you guys have had to learn logs so far? How many of you only have seen logs in the woods? Okay, all right. I actually got a laugh. It was more like a pity laugh for you at home, but I got a laugh. That was a more sincere laugh. Thank you. Laughing at the pity laugh. For those of you who know your log laws, if you take the log of H times OH, that's the same as the addition of those values. We don't have to know our log laws for this, but this is how pH is calculated. It converts a molarity into a number we can handle. Can you imagine the number 9? Right. 1 times 10 to the minus 9, though, is pretty small. So it converts them over to something useful. There is also a POH scale. The POH scale is just as useful, but no one uses it because it's the reverse scale. So if acid is 0 on the pH scale, on the POH scale, 0 is a base. It's a reverse scale. 14 is an acid on the POH scale. It's the same idea, just flipped over. You would take the negative log of hydroxide to get POH. This equation's very easy to use. Let's say that, let's see, who would go with the nickname Butters in here? Now, if you already have a nickname, it's Hoodie. You'll be Butters? Okay. Butters finds out that the pH of his blood is 7.4. So plug that in. The pH is 7.4. He can subtract to find the POH. It's really just an addition and subtraction equation. It's pretty simple to use. So you can easily convert from one to the other. Cool? POH, again, is not used too often. And then the inverse of pH. Take a look at your calculator. What does it also say on the log button in tiny font right above? 10x. Does it say 10x? So that is the opposite of log. It's called the anti-log. It's my favorite. Almost sounds like an environmental group. The anti-log. Okay. So that's what these two equations are. They're called the anti-log, 10 to the negative pH. Why do you suppose that negative sign is there? Yeah, because it was negative log before. So we're just making sure that negative sign reappears in there. Pretty easy equation again. So Butters knows the pH of his blood is 7.4. He says 10 to the negative 7.4, and now you know the molarity of acid in your blood. Yes, there is acid in your blood. Not much, because that's almost neutral, isn't it? It's actually slightly basic. So, fish tank, slightly... Ooh, that's actually slightly acidic. That's the reverse scale. No. Yes. That's slightly basic. That's the reverse scale. You got to be careful with fish tanks. You can easily kill your fish. Math problems. More math problems and all sorts of math problems. So on your homework, Mr. Ram, that's going to be you because of the VCU. So Mr. Ram, you're going to have homework problems that say like, hey, the pH is 12. What's the POH? Which equation would he use if this was the question? The POH is 12. What's the pH? Which equation has pH and POH in it? The bottom doesn't have both of them. Top right. So if the POH is 12, what's the pH? 2. 2 plus 12 is 14, right? Or maybe it says Samantha. Samantha, it says the molarity of hydrogen is 4 times 10 to the minus 5th. What's the pH? So it says, what's the pH? You're either here or here. But then it says the molarity of hydrogen is. That's molarity of hydrogen, isn't it? So you got negative log, the number that is the molarity. And the calculator converts it to pH for you. Cool? So you have to carefully read and then pick the right equation. A little bit more in here about neutralizing acids and bases. Neutralizing acids and bases, very easy. The hydrogen from the acid, shaky. And the hydroxide from the base, guess what they do? They make water. And then the sodium and the chlorine make salt. Very strong, dangerous acid. Very strong, dangerous base. Salt water. They cancel each other out, right? These two are also pretty strong. They're making a type of salt, just not table salt. But every time we neutralize, it's hydrogen hydroxide making water. What if Mr. Ram showed up with 7 moles of acid and I've kind of, what are you, the track star back there says track. I can't read the rest of your shirt. she shows up with 8 moles of base. 7 moles of acid, 8 moles of base, and they mix them together. Are they going to neutralize each other? Why not? There's more base, right? We need them to be equal. This simple equation is making them equal. So you take the molarity of the volume, multiply them so that they're equal. So if we have 0.85, that should be an 8 molar base. That's the base. And then we have a volume. And the strength of this acid, we could solve for what volume of acid needs to be used. How would we solve that math problem? Yep. I'm going to divide by 0.3 afterwards. That would cancel out the 0.3. The answer's 3 point something, but I can't quite remember. I think it was 3.4. Susie? Is it 3.4? Someone with a calculator? I really feel like she's right. Nice job. Isn't that weird how those numbers can kind of like rattle around in your head? Right? Was you the one that did it last period? Ah, that's why. Okay. So, now, let's make this clear. If Gretton over here spills the base on the floor and his hokey buddy wants to neutralize it, pouring acid on the floor is a horrible idea. That's not what you would do. You wouldn't go, hey, look at this spill of base. Let's neutralize it with a bunch of strong acid. Because then there's also a chance of spilling strong acid on yourself. What you end up doing, and we have this, is if you have a spill on the floor, you get out this magical substance called kitty litter. And you pour kitty litter on it, and a reaction occurs. I don't care if it's an acid or a base. It kind of neutralizes it. And then you could scoop up the kitty litter and throw it away. What? We don't throw it out the window. No, you put it in the trash. Well, it just burns it. Either way. But once all of the acid is done burning, it's done. And it's kitty litter, so you're like, so what? It's a lot easier than throwing 1,000 paper towels on it. And especially that since looks like Gritton has spilled 1.2 liters of base on the floor. Come on. That's a hokey problem. All right. Going to skip this one because it's not true. We are going to do a titration probably on the 3rd day. A titration is where you slowly drip an acid into a base or vice versa. We're going to put an indicator in here, and I have picked the right color. Let me see if I can do this right. That's not what I wanted to have happen. Good thing we're not recording this. We're going to put an indicator in there, and as the base drips in, you'll see a drop of pink appear, and then disappear. And then a drop of pink appear, and then a drop of pink appear. And eventually, the whole thing will turn pink. If it's exactly equal, there'll be a light pink. If, however, you add an extra drop, it'll go like Samantha's shirt there. That's kind of a darker pink, right? Was I calling you Samantha a little while ago? Yes, pretending you're still Samantha. It'll go like this dark magenta. You're trying to get the two sides equal. We're going to use an indicator called phenolphthalein. Phenolphthalein. It's right here. You don't often get to say a pH and a TH all at once. Phenolphthalein is no color until you hit base. When you hit about an 8, it switches over. Do you agree 8 is barely basic? Yeah, 7 is neutral. So if you hit 8, it switches from no color to base. The only reason it holds on for a second is when that first drip hits, there's a lot of base in that area, and then it gets neutralized and it's gone. And then it keeps taking over more and more area and then being neutralized, and it kind of slowly spreads. I usually make that into a competition, and I give extra credit to the group that can get the very lightest pink. If you get a dark pink, you've gone too far. You're not equal. You're too much base. Acids and bases, we already talked about the litmus paper, blue for base. We do have a universal indicator that I'll show you later on that goes a whole rainbow of fruit flavory colors. And then these are different indicators we do or do not use. Titration curves are for slow methodical adding. We typically do these, we're doing this in AP Chemistry next week. We're slowly adding sodium hydroxide and measuring the pH at the same time. We're trying to figure out where the equivalence point is from a pH meter perspective. It's kind of a pain to do. And we're out. Questions before I close it off? You have a very important question? Okay, well, let me hear what you're...